Good afternoon, everyone. Myself is Dr. Ajit Kumar. So we'll continue our next lecture. So in the last class, we were discussing about the different instructions of 8051 microcontroller, and we have discussed the data transfer instruction. So that data transfer instruction was not complete. Okay, you see some more instructions here. Okay. For example, the first one that we study is XCH. Okay, this XCH is quite easy to understand. So XCH stands for exchange. Okay. So XCH. So this lecture, the instruction XCH. So this XCH means exchange. Okay, so this instruction is used to exchange. It is used to exchange the two operands. Okay, operands value. Okay, and the syntax is XCH. Right here, register, that is destination register, and another register, source register. And it is going to happen is here destination value will come in source, and source value will come in destination. Okay, so just with example we'll understand this one. So what I'll do is take an example. Suppose that I have written here proof R0 as 3H, and the next instruction is move R1 say A, it has 4 to H. Okay, so what is the first instruction? R0 value will be 3H and A value will be 4 to H. Okay, so if I am going to take XCH A comma R1, so after executing this instruction, the value of A will be the value of R1. This value will come in the place of A. So I'll get here 4 to H, and the value of R0 will contain the value of A. Okay. So I'll get here 4 to H. A is this one 2 to H. R0 is 2 H. Okay. So this is after execution. So quite easy for this instruction. So another thing is that not only register value is going to exchange, it can exchange. We can't exchange the memory. It's not okay. So take this kind of instruction XCH. Have here register, here you can have this. So this is also, so for example, suppose this is your RAM, internal RAM. Okay. And let's say this address 30H, here 3H, and say, so what I do here, I'll just explain this one. So what I do, move in address 30H, the immediate value 23H. Then let's say there is another register A in which I'm going to store 4H, and let's say I will get here CH A comma 30H. So by this, after this instruction is executed, the A will contain the value which is in the address 30, so that is 23H, and the address 30H will contain the value of A. Okay. So value A, which is 4H. Okay. So this XCH is quite easy. Okay. Then we have which one is DA. Let us try to understand DA instruction. It's quite easy. So here the A stands for decimal adjust. So decimal adjust is used to convert the invalid decimal to the valid decimal. Okay, so the DA is used to convert invalid VCD to valid VCD. Valid VCD. Okay, it is used generally after arithmetical. Okay, it is used general after arithmetical or logical instruction. So what is this instruction? DA. Okay, so first of all, let us try to understand this decimal adjust. Okay, so I mean, what is this BCD number? Okay, we have to know this BCD, which is called binary decimal digit. Now, you know, of decimal number 0, 3, 6, 7. This decimal number have the binary, which is 0 is written 0, 0, 0, 1 is written 0, 0, 0, 1, 2 is written 0, 0, 0, 3 is written 0, 0, 0, 4 is written as 0, 1, 0, 0, 5 is 0, 1, 0, 1, 6 is 0, 1, 1, 0, 7 is 0, 1, 1, is 1, 0, 0, 0, 9 is 1, 0, 0. They are binary code for the decimal digit. PCD. So PCD is value for 0 to 9. Any number which is for any number which is greater than 9 is invalid PCD. Okay. Again here in the BCD, okay, BCD also we have types of of BCD, which is called packed. Let's try to understand this one, unpacked BCD. Now in the unpacked BCD, in both cases we have 8 digits. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. In unpacked BCD, lower 4 bit. Okay, this is the lower 4 bit is only containing BCD. Okay, this lower 4 BCD. This upper 8 up 4 bit. Upper 4 bit is always 0. So for example, 5. Okay, say 5. Now this 5 is written using a digit 1, 2, 3, 4, 5, 6, 7, 8. Which this lower 4 bit. Okay, the lower 4 bit is only going to represent the 5. We know this 5 is here. We have seen this 5 is having this 4. Okay, this one 5 is having this 0, 0. So this is going to be here. Okay, this lower 4 bit the upper 4 bit by default zeros. So this is upper 4 bit, which should be zeros. Upper 4 is in BCD. Okay, this is called unpacked BCD. It's called BCD. We have example, for example, 9. So I write here 1, 0, 0. This is a digit in which the lower digit is represent 9, 0, 0, 1, which is 9, 4, 0. So you can see it is not a effective utilization of 8 bit. Okay, it is not effective utilization. Not effective 8 bit because the upper 4 bit is wasted here. Okay, that is why it is called unpacked. Okay. Then we have packed BCD, which represent here upper 4 bit, lower 4 bit represent the individual BCD number. So we have 1, 2, 3, 4 will be one BCD number. Another 4 bit is another BCD number. For example, 5 9. Okay, now this 5 9 is can be written as, you see here, this 5 is one BCD and 0 1 0 1. This is which is 1 0 0 1. So you can see all the 4 bits. Okay, upper and 4 bits are representing BCD number. So that is what is called blank BCD. Okay. So I hope you understood the concept of this BCD classification, unpacked and packed BCD. Okay. Now what we are discussing is case of DA instruction. Okay. So this DA, as I said, it is used to convert invalid BCD is converted to valid BCD by adding 6 to invalid BCD. Okay. So for example, let us try to understand this one. Suppose this instruction move. So A has 6. So I will move has 4. Take this as hexadecimal. Now see here what is going to happen. I am supposed to write this one at A comma R. So you know what it is. We have not discussed about this add instruction. So the meaning of this instruction is this value of A will be added to the value of R naught. It is A plus R naught value and the sum will be replaced in A. So this is the meaning of add instruction that we are just going to study this very soon. So here just add the value of R naught is 4 and A value is 0 6. Just add. So on addition of this 6 plus 4, we are doing here this hexadecimal. Okay, so it's A and this has 1. Now just see this value. This one A is greater than 9, so it is invalid. Okay. To convert this invalid BCD to valid BCD, okay, I'll write here DA instruction. Okay, decimal adjust. Okay, so this decimal adjust instruction A will add, writing this decimal adjust instruction DA, the value of A, okay, will become A plus 6. This is the meaning of this DA. So you are not, I won't say strictly this instruction. Okay, now let's see what is the situation here. So what is going to happen? A 6 will be added to this number. Okay, see here. Let us try to this A, which is 10 decimal. They're adding 6, okay, which is again 6 in decimal. So 10 plus 6 is 16. Now this 16 is in decimal, is in hexadecimal. We have to divide this by 16. So 16 when the 16, 0. So I get this quotient and the value as hexadecimal. So I get 10H. Okay, now this 10H means 0 will be added here. Sorry, 0 will come here. This is called sum. So this 0 is called sum. This 1 is called carry. So this sum we came here and the carry one will go here. So one, now see this has become valid basically. And of course this is also valid basically. Okay, so when you write this DA instruction, automatically 6 is added to the invalid BCD and this leads to valid BCD conversion. Okay, you get the valid BCD number. Then now you can see here we have added 6. The DA instruction has added 6 to the lower 4 bit. Okay, there could be situation when, let's say this situation 4, let's say 7 4 is added with say 6 3. Okay, suppose this is added 4 plus 3 is 7, 7 plus 6 is 13, 13 is, you know, A is 10, B is 11, C is 12, D is 13. So we got here D. Okay, now this have added here hexadecimal addition. So the sum is also supposed to be hexadecimal. Now this one is invalid BCD. Okay, so I need to write here DA instruction. Okay, so DA instruction will do what it will do. This time it is going to add 6 into the D. Okay, so it is going to add 6 only to the invalid BCD. Of course, here 0 will be added. So 7 plus 0 is 7. See this. This is D plus 6. So this D in decimal is 13. This in decimal is 6 only. 6. 13 plus 6 is 19. This 19 has to be converted into hexadecimal number. So just 19 divided by 16, 16 over 16. So we got here 160. Now this 3 is sum, this is carry. So this 3 will come here, carry will go here. So now you can see each one is valid BCD. This, all are valid BCD. Okay. There may be situation when both are uninvalid. Okay, for example, let's consider for example. So suppose 7 is being added with 7 hexadecimal. Okay. Now you know 7 plus 7 is 14. 14 means E. Okay, and 7 plus 7 is 14 means E. Both are invalid. Okay, here both invalid. So if you write here after this instruction, suppose that you have written A, so in that case, what is going to happen? In both invalid BCD, 6 will be added. Okay, this is going to take convert the invalid BCD, both invalid BCD into valid BCD. Now just for the purpose of addition, this 6 plus 14 plus 6 give 20. Because you know this is 14 in decimal, this is 6, 6 plus 4 is 20 in decimal. So this 20 in decimal is equivalent to 16 on the 16 equals to 14H or 6 suffix. So I got here 14 in the hexadecimal, that is 4 will come carry. Now just add this 14 plus 115 plus 6 is 21. 21, if you convert, this will be equal to 50. So this is your correct or valid BCD. This is the purpose of this DA instruction. So I hope this is clear to you. But important. There are also two conditions under which this DA will work. Okay? That is if auxiliary carry is 1, then 6 is added, okay, over 4 bit, okay, by using DA instruction. Okay. Or if CY is 1, then also then also 6 is added to upper 4 bit by using DA instruction. Okay, just let us take example. Okay, suppose that I have written here, say 4 plus 4, 4 plus 4, or 4 plus 4, 3, 4. Just suppose that we are adding this to hexadecimal number. So now this 4 plus 4 seems to be 8. Okay, and you might think that here 6 will not be added. But if you see, I'm not stay. Okay, let's say suppose we have this kind of 0. Okay, so fine, let us consider this one. Suppose that we are adding in binary form. Okay, so 0, 0, 0, 0, 0. Going to show in the carry form. So let's suppose that we are going to add this. So you can see 0 plus 0, 0, 0 plus 0, 0 plus 0 is 1. And now if you are going to add 1 plus 1, you will 0 and a carry will be there to this one. And you can see here, because of this carry, auxiliary flag will become 1. Okay, well, I think I have seen this condition. Auxiliary carry. So you know that AC will become 1 if there is a carry. If there is carry from D3 to D4 bit. Okay, so in this case there is a carry here. So because of this carry, again this number that you got here will be added with 6. Okay, 6 means 0, 1, 0, and then you on what situation if you are going to write DA instruction after this one. So in that case 6 is automatically added and then you get 0. Okay, this one is 0, 1, and then whatever that is. In this situation also 6 is added. Okay, or when there is carry from the uppermost bit, then also your DA instruction is going to work. Okay, so under this situation DA instruction works. So let us come to the next instruction. Okay, that is for this. Okay, let us now start this arithmetic instruction. Arithmetic instruction is addition instruction, okay, and subtraction instruction. Then differential division is supposed to be in this one only, but we have already studied this yesterday. INC I explained you yesterday. Then we have CPL. We understand what is CPL. The value of A, and RLA rotate left. Okay, RLC rotate left with carry, rotate right, and RRC is also there. Okay, RRC rotate right with carry. So let us try to understand all these instructions. Okay, so we'll start from the first instruction, which is called add instruction. Okay, so study now arithmetic instruction. So in the arithmetic instruction, First instruction is addition instruction. Okay. The syntax is, okay, for this the mnemonics is ADD. Okay, the mnemonics is ADD, and the syntax is ADD A comma. Now here this, remember this is destination. So destination is always fixed, okay, which is going to be accumulator. You cannot take any other register or any memory address in the destination when you are going to write add instruction. Okay. So in the case of source, the source operand could be any register value, could be any memory address value, or it could be immediate address value. So any one of these three can be there. For example, suppose that I have written this instruction move a comma has 3h. The instruction is move comma has 34h. Okay. Let's say I've written another instruction also just for the sake of explanation. Suppose that in address 30h I'm storing, let's say 44h. Then I can do one thing. I will write here, okay, add. I'm going to add these two values. So I'm supposed to write add. In the destination always write A. Okay, in the source, this is destination, source value is R0. Okay. So first of all, what is the meaning of this instruction is that this value of A will be added with any one of the value of source, and it will be stored in the A. Okay, that is destination plus source, okay, added, and it is stored back in the destination. And here destination is always A. So A equals to A plus, either it could be register value, memory address value, or immediate value. Okay, this is the meaning of this add instruction. So when you are writing here add a comma r naught, what is going to happen is the value of A will be A plus R naught. Okay, now the value of R naught is 34H. It will be added with the value of A, which is 23H, and it will be stored in the A. Okay, so A value will be 3 plus 4 is 7, and 2 plus 3 is 5. Okay, so this is the answer after execution of this instruction. Okay. Similarly, you can have here another one. Suppose that I write here add a comma. You know that in the memory address 30h, we have transferred this value for 44h. So I can write here memory address 30h. Now, what is the meaning of this one? The meaning of this one is A is equals to the value of A plus the value of memory address 30h. This is the meaning of this instruction. Okay. So I'll get here A is equals to the value of A is 34H, and what is the value of memory address 30H? The value of address 30H is 44. Okay, so you will get this 4 plus 4 is 8, 3 plus 4 is 7. Okay, so this is the value of A after executing this instruction. Okay. So this is, this is the first two cases where the source was register or memory address. I can have also immediate value in the source. So I can write add a comma. Let's say I'm writing here 54h. Okay. Now this is immediate value. Okay, and of course the meaning of this one is a will be equals to a plus immediate value 54h. Okay. So you will get here A is equals to the value of A was 34H. We added with 54H, and then sum will be 4 plus 4 8, 5 plus 3 is 8. So this is the value of A. Okay. So this, the value of A is 8H, which is after executing this instruction. Okay. So this is how this add instruction works. Okay. Now there is another instruction which is ADDC. It is add with carry. Meaning of this instruction is add with carry. Okay, so add with carry, the syntax remains same. Syntax is same. This will be ADDC. Okay, I'll write here A. Okay, always remember that in the any arithmetic or logical operation, the destination is always going to be the accumulator register. Okay, whether you are going to perform addition, subtraction, or any logical operation like and or XOR, in all these cases, the destination will be always A. Okay, A register is accumulator register, and here that source will be any register, any memory value, or any immediate value. Okay, now the meaning of this instruction is A is equals to A plus this one, either register value or memory value or immediate value plus carry. CY carry flag B. Carry flag B. This is the meaning of instruction. Now, why we need this instruction is, suppose, okay, why we need this carry addition. Okay, try to understand this. Let's say that I want to add this instruction. This ADDC is used basically when you are going to perform a 16-bit addition. Okay, 16-bit addition. Okay. Example: suppose that you want to add 16-bit number. Let's say this one. Let us consider this simple: 888. Okay. Let's say I want to add these two numbers. Okay. So if you want to understand that why we need this one, suppose that you are not going to use ADDC instruction. Okay, so in that case, what I'll do is I'll break this 16-bit number. You know, this is 16-bit number. Okay, this is also 16-bit number. Now we know that the register A, R0, R1, all these are 8-bit registers. So I'll have to break down into parts. This one will be added with this one. Okay, so this value of 88 I'll store in the value of A. This I'll store in the value of R0. Okay, using move instruction you can do that one. And then you are going to write here A, D, D, okay, A comma R0. Okay, then what I'll do here, you know, A will be equals to A plus R. Now then when you are going to perform this upper 8-bit addition, so you will do like this. This one again you will have to move in the value of A, this one in any register, let's say R2, and again you are going to write add A comma R2. Okay. Now when you have written this first ADD instruction, there will be no error. Okay, there is no error. But when you are writing the second time addition, then there will be error. There will be error. Let us try to understand this one. See, when you are adding this first 8, okay, so let us try to add this. This is lower 8-bit and this is upper 8-bit. So let us try to add the lower 8-bit. Okay, that is 88H with the 88H. Okay. So when you are going to perform this addition, okay, so let us try to convert them into binary form. So this one is 1 0 0 0 1 0 0 0 1 0 0 0 0. Okay, now let us do one thing. Let's try to understand the addition in case of considering all those this 8. Okay, all the 16-bit. So let us write all this in the binary form. Okay, so 1 0 0 0 1 0 0 0. This one I'll write 0 0 1 0 0 0. This one again 1 0 0 1 0 0 0 0 0 1 0 0 0. Let's try to add this. Okay, I'll segregate this parts here. This is lower 8-bit addition and this is upper 8-bit addition. Now see here what will be the problem here. Okay, so when you are writing this instruction, okay, when you are going to perform this addition using a add a comma r naught, okay, that what is going to happen is 1 0. Let us try to add this 0 0 0 1 plus 1 is 1 0. Okay, so you know 1 plus 1 is 1 0. This is sum, this is carry. So the carry will come here and sum is here. 1 plus 0 plus 0 is 1. 0 plus 0 0, 0 plus 0. And this again 1 plus 1 is, 1 plus 1 is 0. And a carry will come here. Okay, now this carry which is coming here is going to make this next bit addition. Okay, when you are going to add these two, when you are going to add these two number, we see by simply writing add this one a comma r naught, sorry, add a comma r2, then this carry will not be considered. Okay, because we have simply written add, and you know what is the meaning of this add. It is a plus r naught value. Then where is this one value? This one value is ignored. Okay, that is why this is wrong. Okay, so when you have written the first add instruction here, there is no problem. Okay, it is correct. When you are writing the addition for this upper 8-bit, okay, when you are going to add this upper 8-bit, in that case the problem arises because that one is ignored. That is why to perform the addition of the upper 8-bit, instead of writing this ADD, you have to write ADDC A comma R2, and you know what is the meaning of this one. Okay, the meaning of this one is add the value of A is equals to A plus R2 plus CY bit. So if there is any carry because of the previous addition, then there will be 1. Okay, otherwise it will be 0. If there is no carry, then you know there is a flag registers. Okay, you have seen the PSW register. So what is going to happen? We have one carry bit here, CY. Okay, we have other flag bits. Okay, so when you have done this addition, this carry flag, this PSW register will be updated in such a manner that this bit will become 1. Okay, if there would not have been any carry, then this CY bit will be 0. So what is happening? The microprocessor is always checking the PSW register after every arithmetic operation. Okay, and that is why when you are going to write this add next time add instruction, so it is going to check first this bit. If there is carry, then that one will be added here. If there is no carry, then the 0 is added. Okay, so 0 addition means basically no carry. Fine, that is why this ADDC instruction is very important. Okay, so basically it is used when you are adding the 16-bit number. Okay. Then comes our next instruction, which is called subtraction instruction. So in the subtraction instruction, it is going to subtract the two operands. Okay, so that is operand 1 will be subtracted with operand 2. Okay, this is the purpose of the subtraction. And the syntax is, and what is this here mnemonics is, remember, SUBB. Okay, here we don't have SUB instruction as in 8086. Okay, in 8086 we have SUB only. Okay, or SUBB. Two instructions were there. Okay, but here, but in 8051 we have only one instruction, SUBB. Okay, that is, so SUBB means subtract with borrow. If any borrow is there, then that is also taken into consideration. If there is no borrow, then a 0 will be considered as borrow. Okay, and the syntax is SUBB, here destination and here source. So destination is again going to be accumulator register. The source will be any register value, memory address value, or email value. Okay. And the meaning of this one is A equals to A minus either the register value or the memory address value or email value minus borrow. Okay, so this borrow will be either 1 or 0. Okay, this borrow is This borrow is either 1 or 0. Okay, again, try to understand with one example. So, first of all, simple subtraction. Suppose that I want to subtract this value. Let's say 32h with, let's say, 14h. Okay, suppose that you want to perform the subtraction. So you will move this value in the register A using move instruction, that is move as 32h. Okay, and this one you may store in any register or may not register in memory. You either can store this value in any register or memory address, or you can use directly as immediate value. So let us try to take immediate value. SUBB A comma as 14h. Okay. So by using this instruction, what is going to happen? The value of A will be A minus 14h minus borrow. Now here we do not have any borrow, because if there is any borrow because of the previous instruction, then that borrow will be considered here. But let us assume that there is no borrow because of the previous subtraction. So this will be the value of this is 32h minus 14h and minus 0. So this will be equals to 1, sorry, hexadecimal. So let's try to say this 32 minus 14h. This 2 is smaller, so it will take a borrow. Since you are using hexadecimal, so the borrow will be 16. Okay, so this 2 will become 18 now, and this 3 will be subtracted by 1, so it will become 1, sorry, 2. Okay, so ultimately what you will get is 3 minus 1. This has given borrow, so it has become 3 minus 1, and it has become 16 plus 2 because of what it has taken, and here is 1, here is 4. Okay, so you are going to get now subtraction. Now 16 plus 2 is 18. 18 minus 4 is 14. 14 is written as E hexadecimal, and this is because it has given 3 has given borrow to this number, so this has been minus 1 is 1. So this is your answer. Okay, so this is how it works. Again, the same case is there, that suppose you are going to subtract 16-bit number, okay, with another 16-bit number. So in that case, you know 1, 2, 3, 4, 1, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, then 1, 2, 3, 4, 5, 6, 7, 8. Another 8 16-bit number is there. So suppose that you want to subtract this 2 16-bit number. Okay, so you know you are going to store this in the value of A, this in any register value or memory address or immediate value, and then you are going to write SUBB A comma this register memory or immediate value. Then you are going to get answer here 1, 2, 3, 4, 5, 6, 7, 8. Okay, now the problem is, suppose that this number is smaller. For example, here 0 and here 1 was there. So this will take a borrow here. This number, suppose let's say that here 1 is there. So this will give a borrow of here in the, because it is a subtraction in the binary. So you know the binary is having the base 2. Okay, so it will give the borrow of 2. 2 minus 1 is 1, and since it has given borrow, so this 1 will become 1 minus 1, and 0 plus it will become 0. So the thing is, when you are going to perform the next subtraction here using SUB, okay, A comma, let's say any register value or I, in that case this 1 minus 1 that has been done, this bit has become 1 minus 1, so this minus 1 should be considered here. That is why the meaning of this one will become A equals to A minus R or M or I minus 1. Okay, so this one which was subtracted because of the borrow will be taken into consideration in the next subtraction instruction. Okay, this is the meaning of this one. Okay. So the next instruction is addition subtraction. Okay, rotate instruction RL. Okay, RL C or C. So let's try to note this quickly. Rotate instruction, quite easy and quite very easy to understand. So we'll understand the rotate instruction. So there are two types of rotate. First of all, one is simple RR and another one is RRC. Similarly, RL, RLC. So this RR means okay, this is rotate it with carry. This is rotate right with carry. Okay, similarly, this is simply rotate right. Rotate right without carry. And this is rotate left. Rotate left. So in this case, what is going to happen is the bit is going to move in the right direction and in the left direction. Okay, and the syntax, it is going to work on only one operand, that is A register. Okay, so you can write RRA, okay, or RRCA, okay, or RLA, or RLCA. Okay, so it is going to work on only accumulator. Okay, so let us try to understand with the example. Okay, just try to understand. So here, let's say I've written move A comma has to 5h. Okay, now let's say I've written here RRA. Now see here, what is the value of A? A is 5h. Okay, so let us try to write this in the binary form. Is 0 0 1 0. Okay, and this 5 is 0 1 0 1. Okay, now let's try to. Now what is going to happen? Because of this rotate right, all the bit will shift in the right direction. Okay, so here this bit. Okay, what is? Let's try to segregate them. So what is going to happen? This 0 will come here. Okay, this 0 will come here. This one come here. This 0 will come. All the bit will shift in the right side. Okay? And then add, let's say this is D0, D1, this is D7. Okay, so in the place of D7, 0 is shifted. Okay, so here in the place of 0, sorry, this place, because of D0, this D7 bit went into D6 bit. So here in the place of D7, 0 comes by default. Okay, so what I will get is here this bit. Let me write once again 0 0 1 0 0 1 0. Okay, so this bit will come at this position, this 0 will come at this position, this one will come at this position, this 0 will come at this position, this 0 here, this one here, this 0 here. Okay, and by default 0 will be coming at this position. Okay, so this is the meaning of this instruction. So earlier it was 5h. Okay, after RRA, the value is now, this is 0 1 0 1, so that is 5. This is 0 1 0, so it is 2h, so 52h. Okay, so this is the meaning of RRA. Now there is another one which is called RRC. Meaning is rotate right with carry bit. So I'll show you. This is, let's say this is the value of A. So 5, 4, 6, 4 more values. Okay. So let's say this is A and here one C is there. Rotate right with carry. So this bit will go in the CY bit. Okay, and then so this let's say this is D7, D6, D0. Okay, so D7 bit will come in this bit, D6 will come in D5, D2 will come in D4, D4 will come in D3, D3 will come in D2 will come in D1, D1 will come in D0, and D0 value will go in CY, and CY bit will come here. The CY bit will come in place of D7. Okay, this is rotate right instruction. Okay. So in this case, you can see here, this CY flag will play important role. Okay. So let's try to understand this one. Okay. Suppose now in this case the CY flag should be no. Otherwise, you will not be able to know that which bit will come in the place of this. Okay, that is why the CY flag is supposed to know. So what I'll write is, first of all, let us say that the CY flag is 1. Make the CY flag bit 1. You will write here SET, set B C. Okay, the meaning of this one is set the carry flag bit. Set the carry flag. So after writing this instruction set B C, CY flag will become 2. Okay, now after this one, suppose that I have written here move A comma has, let's take the same example 5. Okay, now try to understand what is going to happen after this instruction. Suppose that I have written here RRC 8. Now see here, let us again draw the 8 bits. So 3, 5, 6, 7, 3, 5, 6, 7, 8. So 2 is 0, 0, 1, 0, 5 is 0, 1, 0, 1, and here is carry flag bit. Okay, the carry flag bit is 1 because of this instruction. We have already written set BC, so this is 1. Okay, now when you have written this instruction, this 0 will come here, this 0 will come here, this 1 will come here, this 0 will come here, this 0 will come here, this 1 will come here, this 0 will come here. Okay, and this one will go in carry flag bit, and the carry flag bit will come in place of D7 bit. This is D7 bit. Okay. So after executing this instruction, okay, so after RRC, this bit will become 1. So after executing, the value of A will be, okay, this one 1 0 0 1 0 0 1 0, and see this value is 9, this value is 2. This is the answer. Okay, this is how actually this RRC and RR instruction works. Okay, just here we have this RL. So in RL, the bit shift in the left side, okay, without carry. 1, 2, 3, 4, 5, 6. Okay, all the bit will shift in the left side. So this is D0. D1 will come in the place of D1. D1 will come in place of D2. D2 will come in the place of D3, and so on. Like this. Okay. Similarly, we have RLC. In RLC, all the bits of accumulator will shift in the left side. Okay. So this is D7, this is D0. The D7 bit will come in the CY flag bit, and the CY flag bit will go the D0 bit. Okay, like this. So you can see the left movement, left side movement. Okay, in this case, right side movement was there. Okay, so RL and RLC. So you can take some example and understand this one. So we'll stop here and continue the next lecture in the next class. Thank you.